and welcome everyone to the Varsity Tutors StarCourse series, where this week we celebrate a special holiday that's special and a time to spend with relatives. So what better time than to talk about the theory of special relativity? And if you've used a TV or a smartphone in the last few days, or maybe you are right now, this theory is something you definitely have to be thankful for. And we've got the perfect teacher to break it all down for you. We are live from Armstrong Air and Space Museum with Greg Brown here to break down the history and development of the theory of special relativity and how we may be using it right now to talk to each other, or at least at some point during this afternoon and evening. Now, a couple important things. One, the theory of special relativity involves a lot of our day-to-day communications. Like I mentioned, smartphones. We're going to make sure we communicate a lot through this class. There's a chat box to the right of the screen. Greg's going to ask you some questions to find out what you know and want to know about the theory. And he's also ready to answer a lot of your questions as well. So if you have any questions throughout the program, type them into the chat box. In the last 5 or 10 minutes, I'll interview Greg with your questions so we can get some answers. We also know you're going to want to talk about this at the dinner table on Thursday for the holidays. So if you've got a camera nearby or a smartphone that has one, Greg's the main star of the show, but there's another star of a show you may have heard of named Albert Einstein. We'll give everybody a chance to lean into the screen, take a picture with them so you can show it off at Thanksgiving. So if you've got a camera nearby, that's awesome. Make sure you keep it interactive and use the chat box there. And without further ado, I want to take you live to Armstrong Air and Space Museum to meet your expert instructor for today, Greg Brown.
Thank you, Brian. I really appreciate you inviting me to be a part of this, and I always appreciate it. And thank you for those viewers that are going to participate in this class, if you want to call it that. And so we're going to have a little fun tonight, hopefully, talking about something that's not really very intuitive, doesn't really make a lot of common sense, but it is something that we deal with and that has been a very important part of our understanding of the universe. So we're going to go ahead and I'll share my screen. And hopefully, can everyone see the screen? It says Varsity Tutors, Fundamentals of Special Relativity.
We've got it.
Okay. Now, I do want to say at the outset, all of you folks that are listening in, that even though I'm giving this class, if you will, I am a historian by trade. I am not a physicist. So there may be some aspects of this theory that I am not super versed in or don't have the comprehensive knowledge that you might need. So just keep that in mind for later when we have questions. Okay, so we have a couple of clocks here, and if you've ever heard anything about special relativity, you know that we deal with time, we deal with space-time, we deal with mass, we deal with length of things and distances, but we deal with time, and oftentimes people have heard that time acts kind of weird with special relativity, and we're going to talk a little bit about that here just a few minutes from now. So I've got a couple of objectives for this presentation, this class, and I want to, first of all, talk about special relativity, how it applies, and what it isn't. So in other words, what it is and what it isn't. I want to explain time dilation. Then we're going to have mass dilation or mass increase. We're going to talk about that, length contraction, and we're going to talk about how you add together two velocities that happen to be relativistic. And in this context, relativistic means near the speed of light or at some significant fraction of the speed of light. Okay, we'll be talking about that. And we want to work some problems as usual to better understand the concepts. And then also as usual, I will have questions for you, the viewer. So be ready for those to pop up. So special relativity applied. So we use special relativity as a way of addressing situations involving high speeds. Now, by that I mean really high speeds, okay? Not the kind of speeds you'd see in a jet aircraft, not the kind of speeds you'd normally see in a rocket, at least not the rockets we have, but very, very fast speeds, and also large distances in astronomy and astrophysics. So those are some situations where we might use special relativity, but we also use it as a way of understanding certain electromagnetic phenomena. For example, Faraday's law and etc. and telecommunications. This is something we use all the time, and we've been using for many, many years. And all of us use GPS, right? That is affected by our understanding of special relativity, and the Doppler radar that the local law enforcement officers try to make sure that you're not going too fast on the roadway. So Doppler radar also kind of uses those same principles. Now, we want to say that special relativity is not a theory that proves, quote, everything is relative. You may have heard this. You might have said this, okay? I've said this before, and it's just not true. Special relativity does not mean that everything is relative. And in fact, we're going to talk more about that. Let me see if I can move this down a little bit. There we go. We also cannot say, for example, that special relativity says that we can travel into the past or that wormholes exist, because we can't do that. Special relativity does not help us in that regard. So hopefully that helps a little bit in clearing some of that up. Now, as I said, Einstein's special relativity is often misunderstood. We have a few more misperceptions that we want to cover here at the outset. First of all, a lot of people believe or seem to think that there is a single theory of relativity, and this is not true. There are two basic theories of relativity that Einstein published. The first one is special relativity. We're going to talk about that. And general relativity, we're not going to talk about that because this old guy does not have the capability to do that math. Okay, so special is what we're going to be dealing with. And also people have this idea that E equals mc squared, this really world famous equation. A lot of people think that that has to do with nuclear weapons, and that if it hadn't been for the discovery of E equals mc squared, we couldn't have had nuclear weapons. Well, that's not true either. E equals mc squared is really relatable to all releases of energy, not just nuclear energy. So I want to say at the outset here too, again, the basic concepts of special relativity, they're not intuitive. They don't make common sense. But if you are an average person with some background in algebra at all, you will be able to at least grasp the basic concepts. Okay, so again, we're not going to get into advanced math here. But we are going to be able to show you that most of us, relatively intelligent, have some algebra background, can apply the math to understand at least part of this. And that's good news for me too. So part one is going to be about the publisher of this theory, Albert Einstein, and I'm sure most of you have heard of this guy. So Albert Einstein, very smart guy. He was born in Ulm, Germany in 1879. He was educated in Munich, Germany, attended school, the college actually, in Zurich, Switzerland. He moved there for a while. And while he was a young man in his mid-20s, he was working in the Swiss patent office in Bern, Switzerland. And his building, the building he was in, his office, was located across the road from a train station. And this was interesting and advantageous for him because with the train station comes a big clock that was outside. And he spent a lot of time looking at that clock and thinking about clocks and about time and about special relativity. And he earned a doctorate. And then in 1905, he published a paper detailing this theory. And then he published his general theory in 1915. 10 years later, he worked out the basics of general relativity. He did, in fact, see the writing on the wall when Adolf Hitler came to power in Germany in 1933. And he, like many other people, moved out of that country. They didn't want to be a part of that. They knew something bad was going to happen, and it did. But nevertheless, Einstein moved to New Jersey in the United States and became a member of the staff or the faculty, if you will, of Princeton University. And he spent the rest of his life there. He died in 1955. So he published his theory of relativity, his special theory, under the title of, now this may seem a little crazy, the electrodynamics of moving bodies. That's a little bit of an interesting name. But in fact, when we get more into this and you study it more, this will make a lot more sense. But his theory was very revolutionary. because ever since, this is James Clerk Maxwell we're talking about here in Scotland, ever since his work in the middle of the 19th century, it was known that light was a form of electromagnetic radiation. Radio waves, just like ultraviolet waves, it's violet radiation, it's infrared radio waves, and X-rays, and all those things are actually electromagnetic. So those waves, it had been measured to travel at 300,000 kilometers per second, or 186,000 miles per second, in a vacuum. Now, we all know that this number is the speed of light. I'm sure all remember that. But to put it in more text, think about this. This speed is equal to about 670 million miles per hour. That's pretty fast, right? So if you look up on top here on the left, you'll see this is a diagram of the propagation of electromagnetic radiation moving through space. And the two forms of energy that are shown here is the electric field and the magnetic field, and they are at right angles to each other as they move through space. Well, on the bottom here, where it says, "And God said," this is literally just the four equations that Maxwell collected and expressed to describe electromagnetic radiation, how it moves. And so we can literally say, as the Bible says, when God said, "Let there be light," and then you blurt out all these equations, and then there was light. Okay, so those are the equations that describe the behavior of electromagnetic radiation. Well, the prevailing opinion up to about 1900, or actually about 1885 or so, was that light basically traveled through space, and it was carried upon a material called the luminiferous ether. I advise you, try not to say that too fast. You might hurt yourself. So the luminiferous ether was this strange matter, and it was supposed to spread out all through space, and it was believed that it would serve as the material that light would travel through, and it would be a universal reference frame, or a rest frame, meaning that everything else that moved in the universe would be moving with respect to this material, this ether. Now, if you wonder what on earth this diagram has to do with that, well, this is a kind of a rough diagram of an interferometer. And in around Cleveland, Ohio, in about 1887, there was an experiment called the Michelson-Morley experiment, where these two scientists were trying to figure out if they could determine the difference in speed of light when the Earth is moving towards the sun and when it's moving away from the sun. They believed there was an ether and the Earth was moving through it, and they would hopefully be able to determine the difference in the speed of light, either going one direction or going the other. And they failed to do this. They did not detect an ether at all. So after several experiments failed to confirm this material's existence, Einstein takes this radical step, very revolutionary. In his 1905 paper, he declares the ether to be a fiction. He says it is imaginary. Instead, he says that light travels through empty space at this known velocity. We've talked about it, 186,000 miles per second. And his proposal was that these light waves travel at the speed of light by all observers in inertial reference frames. Now, we're going to define this because you may not have heard that before. So an inertial reference frame just means that wherever you happen to be, you are moving in a straight line at constant speed, or you are at rest with respect to some other reference frame that's like that. Okay, in other words, you're not changing direction and you're not changing your speed. And so if you're in this type of a reference frame and you see some light coming towards you and you measure that speed will be always 186,000 miles per second. So the two postulates, or the two rules, you might say, of special relativity are: one, the relativity principle, and this says that the laws of physics, we're not talking about just the speed of light, the laws of physics are the same for all inertial reference frames. Now, you might wonder, is this Einstein's principle himself? Did he come up with this? Well, actually, no. This is just a principle that he borrowed from Galileo way, way back. Okay, Galileo established this for the science of mechanics, or the study of motion. So now Einstein extends this to the laws of physics all throughout. And so if you were an inertial reference frame, the laws of physics are going to be the same for everyone in that frame. Now, he also says, number two, speed of light is constant, and it's going to serve as a cosmic speed limit. So here he says the speed of light in a vacuum is the same for all observers. Now, this is the tricky part, independent of speed of source or the speed of the observer. So no matter if you're moving or the light source is moving, if you are both in an inertial frame, the speed of light is going to be the same, right? Now, I had to throw this picture in here, not because it has something directly to do with special relativity, but because I happen to like Rod Taylor, and this is a great science fiction movie from about 1960, and he travels back and forth in time. So I just had to throw it up there. Well, scientists, as I said, up through the beginning of the 20th century, believed that there was this ether, right? And that ether allowed the light to travel through and across the universe. And so we all know that sound waves need air, right, in which to propagate or move. And we all know that water waves, obviously they have to have water or they can't go anywhere. And so they need water, and that's that material that the water needs to create waves. But Einstein's very bold step was to insist that the speed of light was the universal speed limit. He says, light travels through empty space at this constant speed, and there's neither a preferred state of motion nor a state of absolute rest. So what he's saying is there's no place in the universe you can go where you can stand there on a rock or on a meteor or on a planet or anything and say the rest of the universe is moving around me. He says that's not the case. No place can you go and say, well, I'm special and everything else is moving and I'm at rest. So that's what he's saying. So this means that motion and space-time are relative to one's frame of reference. And you might be wondering, until now I'm going to tell you, why is it called relativity? Well, because motion and space-time are relative to one's frame of reference. They don't stay the same. They change if you change your frame of reference. So Einstein's theory was very revolutionary because of this and implications like this. And one startling consequence is that the speed of light is measured to be c even by two observers who are moving relative to each other, as long as they are both in uniform motion. So if you look at that, the pair of images there, these two spacecraft or rockets are moving relative to each other. One's coming, kind of straight down, the other's off to an angle. But both of them are going to measure the speed of light to be c, even though they're both moving. Isn't that a little bit weird? Right? So here's a diagram of relative motion. The gentleman in the rear says, he's my wife's second cousin 3 times removed, but he keeps coming back. Okay, relative motion, right? So at any rate, we need to clarify something. The concept of relativity means that to each observer, everything is perfectly normal. Nothing appears out of place or weird. Each person measures the speed of light from their own reference frame to be c, but it also means that each one can say he or she is at rest and that the other one is the one who is moving. Isn't that weird too? That is weird too. So if I'm, quote, moving and I'm moving past you and you're standing on the street corner, I can say that actually I'm stationary and you're moving past me. Isn't that weird? Doesn't seem right, does it? So here's the first question. So make sure you put your thinking caps on, screw them down pretty tight. And so we've got 4 choices. The speed of light is measured to be c in a vacuum. 1, only by observers at rest. 2, by all observers who have instruments to measure it. Well, that would be kind of useful, right? Number 3, by all observers at rest or in uniform motion. Or by number 4, by no one, because it's just too darn fast. And it is pretty darn fast, right? So make your choices, okay? I don't think I've caught anybody off guard yet. No, looks good. You're doing it. You're paying attention. This is always a good sign. But then again, as I always say, my viewers tend to be on the Varsity Tutor channel. They tend to be fairly intelligent people. So take that as a compliment. So actually, the true answer, and most of you got it, is by all observers, quote, at rest or in uniform motion. Now, let me clarify this when I say at rest. So if I say at rest, remember, I'm not saying you're at rest with respect to the rest of the universe. I'm simply saying that if you are at rest with respect to some other reference frame that's at rest with respect to the moving object, this is a little bit tricky, but let's say you're sitting on Earth and you're watching a spacecraft go by, okay? Well, then you're at rest with respect to that spacecraft. Okay, so if that's the case for you, then you can measure the speed of light to be c, and there won't be any problem. All right. So good job in the first set of options. Now, there is a popular belief, as I said, that there's one theory of relativity. There's actually two theories of relativity, and I think I mentioned this briefly, the special theory and the general theory. The two are very different. And again, one of the reasons we're not doing general is because it's just too darn hard. Okay, the math is just really, really advanced, and it's very, very difficult to comprehend. So when I are mentioning that we're dealing with the special theory deals with something called flat space-time. And right away you're thinking, okay, what on earth does that mean? Well, flat space-time, it's Euclidean, the geometry you studied in high school, because there is no major gravitating body that's nearby. And if there's no major mass or gravitating field, then you can treat these equations a lot simpler. And we're dealing with special relativity because we can deal with acceleration. We just can't deal with gravity with special relativity. Now let's look at the opposite of flat space, curved space-time. And in general, the general theory deals with curved space. And this will be a little weird, but according to Einstein, the curve of space-time, presence of mass, is what we think of as gravity, because it affects a traveling body and it affects that body's trajectory and it flips it. It curves it along with that curved space-time. So thankfully, we don't have to worry about that, right? We're just dealing with special relativity. Flat space-time, and that's the difference. So if you're looking at this image up there of the equation, this, don't be fooled by this. This is simply how we calculate acceleration. Acceleration is a vector, right? It has magnitude and direction. So if you're looking at the top, that's literally v, or the velocity. Subtract from that the original velocity, and that is divided by delta t, or the change in time, the elapsed time. So acceleration is literally just change in velocity over change in time. That's all that is. So when we're talking about the special theory, okay, it's called special because it doesn't deal with gravity and usually doesn't deal with acceleration. Most of the time it deals with uniform motion. So that's why it's called special. Hopefully that's helped to clear that up for you. Now, first of all, let's ask ourselves a question. Do these theories mean that everything is relative? I know we've all heard that. I've heard some really smart people say that. No, it's not true. This is not true at all. Einstein himself did not even call his special theory by that name. He said it was his theory of invariance. Invariance as in plural, something that doesn't change. Literally the theory of factors that do not change. And there's a lot of these things that don't change. And according to special theory, several quantities or factors fit this description. The laws of physics, as we said, don't change. The speed of electromagnetic radiation doesn't change. The space-time interval, proper time, electric charge, particle spin, all of these things are invariant. They do not change with the observer's frame of reference. Okay, so hopefully we've kind of ironed that out. I certainly hope so. Now let's talk about E equals mc squared very briefly. So this equation, in case you're wondering, and I'm sure you've heard of it before, this equation simply means that energy and mass are equivalent. Okay, energy is mass and mass is energy. The only difference is you use the speed of light squared here as the conversion factor. So any amount of mass that you find has an associated amount of energy that would be able to be released if you could release it. Doesn't mean that you can release it. E equals mc squared simply means that energy and mass are equivalent. And this is pretty helpful when we talk about certain other aspects of this theory. So Einstein was, in case you're wondering, was not making statements about morality or ethics when he's publishing his relativity theories. just in case you're wondering about that. No, he's not talking about that. Another misconception is that E equals mc squared is foundational to the design of nuclear weapons. Not true. E equals mc squared applies to all events that release energy. So down below, you see there's a mushroom cloud from an atomic or nuclear explosion. And on the right, we see a simple campfire. Okay. In both cases, energy is being released. And if you could release all the energy in those branches and all that, there would be a whole lot more energy released. Okay. So that's all that's really saying. So part two, this is now Einstein himself here on a bicycle. He obviously is enjoying himself there. So now we've talked about the differences between special relativity and general relativity. And hopefully we've dispensed with this notion that relativity means everything is relative. There's no standards. That's nonsense. We can now hopefully dive into the special theory itself. And this is where it gets kind of fun, I think. So first of all, we're going to talk about time dilation. So time dilation means that a moving clock runs more slowly when viewed from a frame of reference that is not in motion with it. Okay, now that may sound a little bit complicated, but it's really not. So if you're on Earth and somebody is flying past Earth in a spacecraft, let's say, and let's say you could zoom in and look in the window of that spacecraft and look at the spacecraft clock, that clock, if that spacecraft is moving at a significant fraction of the speed of light, you would see that spacecraft clock to be moving slower than your clock. Okay, that's basically what that means. Now, this, again, sounds pretty strange, but let's see how this situation affects time. So we're going to set up a scenario. Now, I know some of you are going to say, oh, no, not a story problem. I hated those. Well, I didn't like them too much either in school, but this is what we do in physics. We set up a scenario, and this helps us to understand a concept. Now, this scenario we're going to use is a popular one, and it's called the twins paradox. Maybe you've heard of it. So we're going to talk about a pair of identical twins, and they can be male or female. It doesn't make any difference. One of them is going to get in a spacecraft and travel to a distant star. And the other one's going to be on Earth, sitting in their house and doing their thing, and they're going to keep track of the time. And I mean, literally, the calendar, okay? So special relativity indicates that if the astronaut twin travels at a significant fraction of the speed of light, he or she will return from the trip younger than his or her sibling. And you're probably thinking to yourself, say, what? What are you talking about? If you're twins, you're the same age, and that's it, right? No, that's not it. Okay. So here I'm just throwing up a picture of U.S. astronauts or former astronauts. Now they're both retired. Scott Kelly on the left, Mark Kelly on the right. And these guys both made several trips to the space station. And so we're going to kind of keep these guys in mind here for the twins. Now, let's tackle this problem for ourselves. We're going to see just firsthand the strange things that can happen to space and time according to special relativity. So maybe you should buckle up. Okay, because this is get pretty wild. So we're going to say that the traveling twin is going to visit a star system 10 light years from Earth. Okay, 10 light years from Earth. Now, let's make sure we all understand this. A light year is not a measure of time. It's a measure of distance. And in fact, a light year is the distance that a light wave or particle travels, let's say from Earth, in one Earth year. So you might be wondering, well, how many miles is that? And it turns out it's about 6 trillion miles. That's a long way. All right. So this twin, the twin's going to travel is going to go 10 light years away. There's a planet there or a star, and they're going to travel at a velocity of 0.8 c. Okay, right away, somebody's saying, all right, what does that mean? It simply means 80% of the speed of light. Anytime you give a fraction and you have a c after it, you're talking about the sort of thing, we're talking about the percent of the speed of light that you're moving. So 80% of the speed of light, this person is going to travel. Now we have an equation. Oh no, you're saying we always have equations. Well, these equations are pretty simple. So we have an equation to deal with this scenario, and it looks like this right here. Look how simple that is. T prime is equal to t multiplied by the square root of 1 minus v squared over c squared. How simple that is. So t, the t that's right next to the square root, or that radical there, is the elapsed time for the earthbound twin, okay? And t prime is the elapsed time for the traveling twin. And v, of course, is the velocity of the traveling twin's spacecraft. Okay, this is some simple stuff, folks. And it's a good thing it is, or I wouldn't be able to understand it, okay? So don't feel bad, all right? I'm no smarter than you are. All right, so in order to solve for t prime, we're going to have to establish a value for t and for v. So we're just going to make it up, okay? So to find t, we use a simple equation. This is from probably 7th grade physics. It's time is equivalent to distance divided by velocity. T is equal to d over v. Couldn't be simpler, right? So if the traveling twin's journey is going to cover a distance of 10 light years, as we said before, and his or her velocity is 0.8 c, then we plug those values into the equation and we solve for the time. And it turns out that if we divide 10 by 0.8, we get 12.5 years, 12 and a half years. So the time taken for the traveling twin to reach the distant star is measured to be 12 and a half years by the earthbound twin. So the person on Earth is flipping through their calendar every 30 days and on, and they do this for 12 and a half years. That's a long time to be sitting in a spacecraft traveling, isn't it? Okay. So 12 and a half years passes for the person at home. Now we want to find out how much time passes for the traveling twin. So we're going to plug the 12.5 into this equation. See that on the top there? And we're going to square the 0.8 c. Okay, so that gives us what? 0.64 c, right? Actually, it's 0.64 c squared because we're squaring both terms, the 0.8 and the c. So we square and we get 0.64 c squared, and we've got 12.5 multiplied by the square root of 1 minus 0.64 c squared. Well, we're going to subtract 0.64 from 1. We're going to get 0.36. Now, we could have just dispensed with the c squared at the end, but we use the c squared here because we're keeping track. It's like housekeeping chores, right? So we want to make sure we don't make a mistake. So what we can do is we can divide c squared by itself and we get 1. So we just do away with it. All right, they cancel out. So we then take the square root of 0.36. Now, all the people that are watching can probably say in their head, oh, the square root of 0.36 is 0.6. Okay, it's just like taking the square root of 36. Same thing, right? So we get the result of 0.6. So all we need to do is multiply 12.5 by 0.6. This gives us 7.5 years. These are not hard calculations, right? Now, you're probably thinking at this point, wait just a cotton picking minute. Are you telling me that only 7.5 years has passed for the traveling twin, while 12.5 years have passed for the earthbound twin? Yes, that's what special relativity indicates. That's trippy. But keep in mind, this is only half the story because the calculation we just did only gives us one-way trip time to the star out there. We need to figure out the round trip time. So we're going to multiply both those values by 2. So the difference in time is going to be, are you sitting down? Are you ready for this? 15 years. So when the traveling twin returns, he or she will be 15 years younger than his or her twin who stayed behind. Whoa, what is that all about? That doesn't even seem like it's possible, does it? Well, that's what special relativity tells us. It's a very strange theory, right? So here we have another diagram, or I guess an animation, a picture of the two twins. In this case, these are brothers. Okay, so on the left, they're shaking hands because they're saying goodbye to each other. So the one on the left is going to take off in the spacecraft, and one on the right is going to stay home. On the right, we see he's returned, and look, he's got less hair on the left, but look at his brother. Look at his brother. Think of it this way. If the guy who left was 50 when he left, his brother was 50, and then when he returned, he's 65, but his twin is how old? 25 years older. Yeah. Now, here's the crux of this. The traveling twin was moving at a significant fraction of the speed of light, 80%, while the earthbound twin was at rest with respect to its twin. So the earthbound twin was sitting on the Earth, and we don't want to go into this too far in the weeds, but the Earth is technically not at rest because it's accelerating in orbit. But what we can say is we can basically ignore the fact that the Earth is orbiting the sun because its velocity and its acceleration is so tiny and so puny compared to the other one. That's literally the case. Okay, we can ignore the Earth's motion. Now, when we say that moving clocks run slowly, this is a little bit of a trap. I mean, we don't want to get trapped into this idea, this false idea. We're not saying that all clocks, because they're moving, we're not saying that some force or some sticky stuff is kind of slowing down the hands of the clock and not allowing them to move right. That's not what we're saying. So what we're saying is, to an observer at rest, the traveler's clock is moving slower. But here's the kicker, like I said earlier, the traveler could claim the observer's clock is the one that's moving slowly. That just seems to be impossible, doesn't it? It seems to be a real conundrum. How could this possibly be? Now, in this case with the traveling twins, you might be thinking, if you're ahead of me, you might be thinking, wait just a minute, Einstein Jr., that can't be right, because we just talked about this. The traveler could claim the observer's clock is the one moving slower, and the one on Earth can say, well, the traveler, my brother or sister, has a clock that's moving slower. But there's a difference in the motion of these two. Remember what happened. The twin that left and traveled that 10 light years traveled at, we're going to assume it was a constant speed in a straight line. Technically, it wouldn't be, but we're going to assume they did. However, when they got to the star or planet that they wanted to get to, they had to accelerate because they had to not only slow down, turn all the way around and speed back up. So their state of motion did change, whereas the twin on Earth, that person's state of motion did not change. Okay. And another way to see this is really a bizarre concept, and we're going to talk more about it in a minute. Another way to see this condition or this situation is the traveling twin did not travel the entire 10 light year distance. No, because they didn't travel that far. What do you mean? You're probably thinking. Because of length contraction. And we're going to talk about that in a few minutes. So that's relativistic time dilation. Really bizarre. Really bizarre. Okay, here's our second question. Remember, you're supposed to keep your thinking caps on, right? So in the twins paradox, why does the twin on Earth grow older than his or her sibling? Number one choice is his or her genes are defective. Okay, that might be an answer. Number two, time has passed more slowly for the twin moving at a high fraction of the speed of light. Okay, how about number three, the twin at rest is not getting his or her exercise? Maybe. And number four, the older twin lacks a positive mental attitude. Well, that can make you grow old, right? You got to keep that positive mental attitude. All right, so make your choices, and we'll move on. So, all right, great. You folks are paying attention. Boy, you must have had your coffee or something, right? It looks like you're all pretty sharp there. So that's terrific. All right, we're going to move on. Number two is the correct answer. All right, now let's talk about this, because this is really tricky. All right, mass dilation, sometimes called mass increase. Now, what I wrote here, okay, don't hold this to be gospel. So there is a commonly held misconception I wrote regarding mass and relativity. We often, when we study this topic, we hear that mass increases as the velocity increases. And I've said, however, this is incorrect. Well, I don't want you to think that I'm pronouncing judgment on this view, because there are actually some physicists who would maybe disagree with this in the details, right? And we're not going to go into this in a lot of length or in a lot of comprehensive manner, but for the most part, what we want to do is at least provide an explanation relative to rest mass. So there's something called relativistic mass of an object. There's also inertial mass, and there's gravitational mass. Well, all those are the same except for relativistic mass. So for practical application, the only mass we're going to be concerned with is rest mass. In other words, if you go out in the driveway and you look at your car and it's sitting there, that's the rest mass. However much it weighs, right there sitting there, not moving, that's its rest mass. So a ball on the ground, a pile of bricks in your yard, any of that, that's all rest mass. But since energy and mass are equivalent, remember we just talked about E equals mc squared, we can imagine that as energy of a body increases, the inertial mass increases. We can imagine that, right? Because inertia is literally the resistance to the change in motion of an object. So conceptually and mathematically, you can say the mass increases as a body gets faster and faster, closer to the speed of light. But this is not an actual physical change. So don't look for any additional matter. No extra atoms are coming in and sticking to that object. You know what I mean? That's not what's happening. So let's backtrack a little bit to this second paragraph. When a body is in motion, its momentum increases with its velocity. So the momentum of an object is its mass times its velocity. So a momentum, that amount of mass times energy, or mass times velocity, is going to increase if you either increase the mass or the velocity, right? But the rest mass, this amount of stuff in that object sitting there, is not going to change. Not really. It's what we might call a Lorentz invariant, the rest mass, okay? So hopefully that is something that's maybe a little more clear. Maybe not, I'm doing my best. All right, so if we want to make a body, let's say a spacecraft, we want to make it go faster and faster and faster, we've got to use a force, and a force is a push or pull, right? So in physics, F, or force, is equal to the mass of an object times acceleration on that mass, or I should say how much that mass accelerates or speeds up or changes direction. So as force increases the velocity of a body, it increases the object's momentum and requires more energy to accelerate even further, which increases its momentum again. And this is a vicious cycle. And really, we're going to talk about kinetic energy and momentum. So an object would have to have nearly infinite energy as it approaches the speed of light. And this is one reason why no material object can be accelerated to the speed of light or beyond. Now, the special relativity theory does not say that objects cannot move at the speed of light, because photons certainly do, right? It just says you can't take an object that's physical and moving less than the speed of light and push it up to that speed. So we want to show a couple of equations here. Relativistic kinetic energy, that's on the left, and then relativistic momentum. So we have a equation that we deal with. We want to calculate an object's kinetic energy, or energy of motion. And the classical way of doing that is to say you take one half times the mass times its velocity squared, and that gives you its kinetic energy. But if you're talking about relativistic kinetic energy, you're moving so fast that you're moving, let's say, half the speed of light or something, then the kinetic energy the body possesses is going to be calculated by this particular term here. Now, if you look over to the right, you're going to see P with a sub V there. That is relativistic momentum, because P is momentum. And so you can see that the rest mass, that's a M sub 0 on the top there, multiplied by the velocity. But you have to divide by this term here, which we've seen before, haven't we? We've seen this before. So 1 minus V squared over C squared, and take the square root of that. So the relativistic kinetic energy and the relativistic momentum are both different than the classical or normal, what we call the normal types, okay? Now, I'm going to show you the factor that changes all these things, that makes them different than what they would normally be. So if you look at, the upper equation, that is relativistic momentum is equal to this weird Greek letter gamma multiplied by the rest mass and the velocity. Instead of just mass times velocity for momentum, you have this gamma term. So there's the gamma term. But what about that gamma term? Well, let's look at it down here. That gamma term is equal to 1 divided by this term we've seen several times. 1, that's the square root of 1 minus b squared over c squared. So this is called the Lorentz factor. That's Lorentz, L-O-R-E-N-T-Z, the Lorentz factor. And this factor allows us to calculate all these weird situations when we're talking about time and length contraction and all that sort of thing. Okay. So here's another question. I threw it at you pretty quickly. So keep your thinking caps on. The question is, how does increasing an object's velocity create more mass? That is a good question. So the first choice is, strictly speaking, it can't. Kinetic energy is increased, momentum is increased, but rest mass doesn't change. Or number 2, as velocity is increased, the spacecraft collides with more and more particles, which makes the spacecraft heavier. How about number 3? Like a video game, if you go faster, you can collect more treasure. And of course, treasure has mass, right? Or number 4, hypervelocity drags more space-time with it, adding to the total mass. Now, this is a little tricky, and I'm seeing a few that got a little bit off track with that, and I apologize. But this is, after all, kind of a quirky sort of a concept, kind of hard to grasp. So most of you got it. And thank you very much for paying attention and being really active viewers. I appreciate that. So that number 1 is the actual answer. Again, rest mass does not change, but if you view it as inertial mass or even gravitational mass, you can say maybe that's what we think of when we believe that the mass increases. But really, in a real practical sense, again, no extra atoms are coming and attaching themselves to it. So hopefully I didn't make that too confusing. Now, if we want to talk about 2 objects and they're both moving, right? They could be moving the same direction. They could be moving toward each other. But if we want to add their velocities together, there's a very easy, very common way we do that. Learned it way back in elementary school, or probably at least junior high. So when you sum or add together the velocities of 2 moving bodies under normal circumstances, we use a very simple formula. Literally, it's V is equal to V1 plus V2. And you can call this the Galilean velocity addition theorem. You can call it the Newtonian or the classical method. This is just something we do all the time. You take the speed of the first body, add it to the second body. The total speed is the sum of the 2. This is really simple as can be. But if 2 observers in different reference frames are measuring the velocities, or if the velocities are large relative to the speed of light, we have to use a different method. The normal method won't work. Now, we're going to imagine a sailor. Actually, he's an aviator. He's a naval aviator. Frankly, this guy's just having way too much fun. All right, but he's on a deck of an aircraft carrier. And we're going to say he's riding his bicycle on the deck of the ship. And if he is riding his bike at 20 miles per hour on the deck, while the ship is moving at 25 miles per hour relative to the shore, the sailor is moving at a speed of, well, add them 2 together, 20 plus 25, 45 miles per hour relative to the shore, right? And that's simple Newtonian physics. Now, somebody in the audience may say, well, wait a minute, ships don't use miles per hour, they use knots. Okay, well, right, I know that, right? But I don't want to entangle everybody in that, because then some people aren't going to know what that means. So we're just going to use miles per hour. Okay. So this guy who's having a blast is moving with respect to the deck 20 miles per hour, and the ship is moving at 25 miles an hour relative to shore. So he's moving relative to people on the shore at miles per hour. So again, this is your classical method of adding, right? But as we've seen, special relativity is different. We can't do it that way. So let's suppose we want to add the velocities of 2 spacecraft together, and they're very, very fast. So we're going to tweak the scenario of the bike riding sailor just a bit to adapt it to our purpose here. So, yes, we have another story problem. Okay. Sorry, that's just that's the way we have to do it. So we're going to say we have a spacecraft traveling at 0.8 c. Where have we heard that before, right? 80% of the speed of light relative to some inertial frame, let's say a person measuring their speed on a planet. And then at some point, an astronaut's going to come out of the nose of the spacecraft, and he or she's going to wear a rocket pack, and that rocket pack is going to fire them, and it's going to shoot them up to a speed of 0.5 c, half the speed of light relative to the spacecraft. Are you sort of getting that in your mind there? A spacecraft, and then it's moving at 80% of the speed of light, and then there's going to be like a little hatch on the front, and a little astronaut's going to come out, and they're going to be moving at 0.5 c, okay, relative to the spacecraft. So if we took these speeds and we added them up using classical physics, we're going to get what? A weird answer, aren't we? We're going to get 1.3 c. That's faster than the speed of light. Einstein says that's not happening. It's not going to happen, right? So faster than light, according to that inertial frame, just doesn't work. By the way, I had to throw this picture of Bruce McCandless out here floating around in 1984 outside the Space Shuttle orbiter. And this gentleman has a manned maneuvering unit on his back, and he's able to move around independently of the spacecraft. So he becomes his own spacecraft. This is kind of what we're talking about, if you can imagine that. All right. Is it possible to move faster than the speed of light? Well, in science fiction, they do it all the time. I'm a big fan of Star Trek, the original series, and they do it all the time. Okay. But according to Einstein, it's not possible. Remember what we said earlier? One of the tenets of special relativity is that c, the speed of light, is the cosmic speed limit. It says no material object can be accelerated to the speed of light, nor can it be made to go faster than the speed of light. So if that's true, how in the world are we going to add these two velocities together? Well, I have an answer for you. It's this equation right here. So this equation takes the original classical version up here, Galilean's theorem, and says that the total velocity is v1 plus v2. However, this is a little different. Beneath this division line, we have 1 plus the product of v1 and v2. We multiply them together, and we divide them by what? The speed of light squared. You're getting used to seeing this right by now, right? All right, so if we want to solve this equation for the total velocity, we're going to see another really weird consequence of special relativity. So let's go back to the spacecraft and the astronaut. And we're going to label the spacecraft speed, which is 0.8 c, right? We're going to label that v1, and we're going to label the astronaut speed, half the speed of light, as v2. Now let's plug in our values. And as you see there, it's simple math. 0.8 c plus 0.5 c divided by 1 plus the product of 0.8 c plus, and 0.5 c divided by c squared. And we're going to get 1.3 c divided by 1 plus 0.4 c, all divided by c squared. So as we saw the last time, the c squareds cancel out, and we're left with 1.3 divided by 1.4. I told you this was simple math, right? We're left with a total velocity of 0.93 c, 93% of the speed of light. So even though straight addition results in a number larger than 1, a speed faster than light, which we can't have, a relativistic summation, like we just did, results in a number less than the speed of light. Isn't that bizarre? That's bizarre. But it's interesting, right? I think it is. All right, we're going to talk about collapse time is measured to be shorter for a moving body as measured by a stationary observer. So a body's relativistic length will be measured to be shorter than its rest length. And this is another weird thing. And we're going to see how weird it is in just a minute. So this equation here lets us calculate that length contraction. We have L, which is the relativistic length. And remember, relativistic length means its length when it's moving at that speed that's somewhat near the speed of light. So the relativistic length is equal to, and this L sub O is just its rest length. Rest length multiplied by this. And again, by now, you're probably really comfortable with this term, the square root of 1 minus v squared over c squared. And I'm really thrilled that this is a simple equation. for my sake and your sake. All right. So, and this is my Starship Enterprise here. So, at different speeds, what happens to that spacecraft? So, up the upper left at the top there, we see that it is at rest. It's not moving relative to the speed of light. And then on the right, it's moving at almost 60% of the speed of light. You notice it's a little squashed from front to back, but it still doesn't look that bizarre. And then down to the left, the speed is 20% of the speed of light. You notice that at that speed, the spacecraft doesn't even appear to be different at all. It's not really different. It's almost no difference. And yet you look over to the right, and at 80%, basically, it is really squashed. Okay. Then you go back down to the left, and it's 40%. So it's still not that much different from the original. But look at the ridiculous cartoonish appearance of it when it's moving at 99% of the speed of light. It's squashed so dramatically that it just looks ridiculous. Okay. Now, these objects, anything that's moving that's fast and it gets contracted, it's oriented in the direction of travel. So it's not from top to bottom or side to side. It's only from front to back because that's its direction of motion. Crazy thing. And I alluded to this before. I somewhat stated this, but true inside this spacecraft, there is nothing wrong. There's nothing. It's simply the way it is. Okay. Their clocks are running normally. Everything is the proper size and the proper thickness. Not changed at all. Very strange. All right. So this is my last question, and I'm going to ask it as a true and false. So get your on. If two observers are each traveling at constant straight line, both of them can claim that they are the one that's and the other observer is moving. Think back to principle. Okay. There's no rest frame. There's no particular speed. So if they're moving at a straight line at constant speed, or whatever, they can both say, I'm at rest and you're moving. Is that true or false? Okay. And once again, most of you really nailed it. You're really, really a good audience, good class, because the answer is true. As weird as this may seem, it's true. All right, now we want to cover this kind of briefly, but Brian mentioned to begin with that there are some things that special relativity has to say about everyday life and actually has contributed to our understanding of things that we use. So engineers must account for relativistic effects. Electrons are moving back and forth. Mostly a lot of it's photons, but they're moving back and forth from satellites to the ground to satellites and satellites back to the ground. So we can have a proper functioning telecommunications network. We all rely on our cell phones, right? And if we didn't have satellites up there to relay signals, we'd be in trouble. We wouldn't be able to talk to anybody, at least not very much. So cell phones use satellites to relay signals that are moving either at the speed of light or very close to the speed of light. As a result, time dilation is experienced, and so ultra-precise clocks must be used to make sure everything is lined up. And in the old days, back when I was young, the old TVs we had a cathode ray tube. It was a big glass squared tube in the front and then kind of a cylindrical tube in the back. And at the very end, the back, there was a little device called an electron gun, and it shot electrons at very high speed toward the inside of that screen. And those electrons would strike the inside. It's coated with phosphor. It's a type of chemical with phosphorus in it. And because their speed is about 30% of the speed of light, the electrons are literally traveling a shorter distance than they would if they were slower. Think back to the Starship Enterprise we just talked about. Whether you're talking about an object that gets squashed or whether you're talking about a distance, it's the same. Okay. Hopefully I sort of made that plain to you now, even if I didn't make it plain before. But length contraction isn't just about objects that get squashed. It's about distance from here to the store downtown or whatever. Anything, any distance at all, any spatial extent gets contracted. So because these electrons are traveling significantly somewhat near the speed of light, they don't travel the same distance. That tube, if it's in reality, or let's say if it's measured by you at rest to be 2 feet long, to the electron, it's maybe 1.5 feet. And if the engineers did not take account of this, those electrons would be striking at the wrong space, and the picture would be blurry. So we wouldn't have a good picture. Okay, so that's something to think about. Also, GPS functions, due to an understanding of both special and general relativity, the signals travel at c. There's time dilation going on, but there's also differences in gravity between Earth and orbit, and so there's a little bit of a gravitational time dilation there. And we also talk about the Doppler effect, and we're really going to gloss over that in this talk because I just don't have time to go into more and different concepts. But time dilation is affected somewhat by the Doppler effect in certain cases. So that's just something we just don't have time to talk about. All right, so I want to conclude by saying that special relativity, that we've talked about it, and if you had certain views about it or certain opinions about it or beliefs, hopefully if they weren't correct, hopefully those have been corrected. And we tried to talk about what special relativity is. We tried to talk about what it isn't. And I just want you, I'm going to reiterate that I'm not a physicist, and there's a lot more that I couldn't cover here. Okay, a lot more. I just couldn't cover it all, and I don't understand it all myself. And the number 2 thing I want you to remember is the core principle of special relativity is that the speed of light will be measured to be c. Remember what that speed is, by all observers in uniform motion in a straight line at constant speed. As long as you remember that, you're doing pretty well. So Brian, I'm going to turn over to you and let you talk.
All right, perfect. Well, hey, thank you. I my head is spinning pretty close to C at that speed here, but I guess I don't know if it factors. Maybe it's general relativity. Time flies when you're having fun, and this was a blast. I think everyone in the comments can attest to that. So huge thanks, Greg, for taking such a complex topic, breaking it down to simple math. And we've got a couple. We have a little bit of time. We'll dial it. We'll say we're moving fast enough that we can cram an hour's worth into an hour and 10 minutes or so for everybody to get a couple of your questions answered. One of the things we mentioned we wanted to do is give everybody an opportunity to lean into the screen and take a picture with the star of the show, who really is Einstein, although I might argue for Greg as well. So Greg, if you want to flip over to the picture of Einstein, it's a great place to be able to show this off for all your friends. And Greg, if we flip our cameras off, they'll get a clean picture with Einstein. We'll give everybody about 10 seconds to do that, and also ask your questions, because we're going to pop Greg back on in just a moment and get those answered for you. All right. One of the most common questions is this being recorded? If you didn't get the perfect picture, you can always come back to the recording. We'll send it out to you tomorrow morning. Make sure you got an Einstein picture to show off over Thanksgiving. The other thing, I've always just been fascinated. I feel like if Einstein were alive, he would be so fascinated by the device you were using to take the picture. So it's just good that we integrate him into technology like live streams and digital photos and all those kind of things. If we've got time for a couple sets of questions here, Greg, I'm going to bring us full screen here so everybody can see both of us together while I'm asking and you're answering. One question came up, a lot of fascination, as I'm sure you predicted, with the twin paradox, and quite a few people were asking, hey, even, like we mentioned, relative mass versus, rest mass and all those kind of things. Would the twin fully physically be different? The one that moved at high speed and is 15 years younger, would that twin live to a different year? Would that twin look differently? I mean, we saw in the image there, one had baldness, gray hair, all those kind of things. The other looked pretty young. Basically, from that point on, are they two completely different ages and will live two completely different lives? Is that true?
Yeah.
Wow.
Yeah, one of them has been exposed to acceleration that the other one has not been exposed to. Their frame of reference has changed. Um, their state of motion has changed. So they literally are, in that case, uh, 25 years or 15 years difference, depending on how you calculate it. So that's significant. And that's huge. It just seems very strange that something like that could really happen. But given those conditions, it really could, according to special relativity. Very
Fascinating.
weird.
So Ponce de Leon almost found the fountain of youth, just wasn't moving fast enough
Right, it
to
wasn't moving
figure it
fast
out.
enough.
So
Yeah.
little better sail, a little more wind may have figured it out. So cool. Thank you for that one. Another one that I thought was pretty fascinating, bringing it to to Earth's neighborhood, is you mentioned we can use special relativity for our purposes here, kind of flat space time, and you need a mass with enough gravitational field force. I forget the exact terminology. How does Earth factor in? Is Earth big enough to lend itself to general relativity, or if not, what bodies in the solar system that we would know of are big
So
enough?
this is a great question, and I have an answer. So in 1919, there was a British astronomer named Arthur Eddington, I believe it was, and he wanted to see whether or not he could detect any difference in the photons that are traveling from the sun or from a star, and if those photons are bent at all by the presence of a massive body like our sun. So during a solar eclipse in 1919, he measured the light from a distant star that was normally behind the sun at that point, and he was able to see that star because of gravitational because of the acceleration that gravity field puts on that light. Believe it or not, the light was bent by just exactly the same amount that Einstein predicted. So we can say that even light, which has a rest mass, is actually affected by gravity, and its trajectory is bent. And this is more in line with general relativity. So again, in general relativity, gravity is not a force like in the classical Newtonian world. It's the effect of curved space-time, and space-time is curved due to the presence of mass. And it has to be a big mass, so like a star or large star, or even a galaxy. There's gravitational lensing that astronomers notice, and they can measure it because light from distant galaxies is coming through, and they're being bent by other objects in the way, big massive objects. So that's a really amazing thing. Now the other thing is, scientists have been able to measure the distance between clocks that are on airplanes that are flying high distances above the Earth, and those same clocks that have been a pair of clocks, they've been synchronized, and the clock on Earth is running at a different time slightly than the one that's up on the airplane. So those things really are measurable effects.
That's so fascinating that theoretically the math works out, and then we can run experiments in our own neighborhood here to be able to prove it. Speaking of the neighborhood, we got a long weekend coming up. People may be in the neighborhood of Central Ohio. I think I was telling you before class, many Thanksgivings I've driven right past the museum there. So for those who find themselves in Central Ohio over the weekend, over the holidays, at any point in 2024, I know you're with Armstrong Air and Space Museum. We love our partnership and being able to do all these kind of classes. What's going on over the next few months at the Armstrong Museum, and what can people expect to see if they come and visit?
Well, we've got a lot of stuff going on. Throughout the year, we have various events, but of course, the big upcoming event is the eclipse, the total solar eclipse that will be occurring in April of 2024. And Wapakoneta, that's where our museum is located, is in the path of totality, which means that the solar eclipse will be viewed by anybody along this path. And you can look up the map on our website or many places online. So for about 4 minutes, just under 4 minutes, the sun will be completely obscured by the moon, and you will be able to take off your safety glasses and actually look at it. And then right before the sun comes back out from behind the moon, you got to put your glasses back on. But that's going to be dramatic. That's going to be a dramatic event. We anticipate several thousand extra people coming. And on our website, armstrongmuseum.org, we actually have a list of the scheduled events for that weekend. That will be, let's see, the eclipse is on the 8th, which is a Monday, but we're going to be having special events from Saturday, which is the 6th, Sunday, which is the 7th, and then the 8th, the eclipse itself. So that's a big deal coming up. We have all kinds of things planned. So if you want to know what's going on, just go on our website, again, armstrongmuseum.org, and check it out.
What better place to be able to observe a lunar eclipse than at the museum for the first solar eclipse, but the moon is involved. At the place that Neil Armstrong's hometown. Now that is fascinating. You mentioned the website. We're going to put that up on the screen here in just a second. Okay. I may need to look into flights, Greg. This sounds like what an awesome opportunity. So thank you for sharing all the insights on the theory of special relativity with us. Thanks to all of you out there for incredible questions, participation, all your answers to Greg questions and everything as well. And hopefully everybody does have an opportunity to check out the museum. Here's information to connect with them on social media, to go to the website to check out the path of the eclipse, all the other exhibits there, plan your trip. And like I mentioned, we do these events pretty frequently with Armstrong Air and Space Museum and with Greg. So hopefully he'll be back here soon, and hopefully we'll all see each other around the time of the eclipse. In the meantime, everybody have a great Thanksgiving, and I'll see everybody back here soon.
Thanks, you too. Everybody. Thank you very much.